In the previous lecture, we ran this command, isn't it? You can see that there are a lot of weird sections. And you can see that the C library introduces every function as a separate text section. At the end of the day, what we can do is we can club all these separate text section of different functions into a common text section. We can do that. It's better to arrange like that. Arrange all separate RO data section into a common RO data section. For that, we have to edit our linker script file. Let's go to the linker script file. And what I can do here is I can add one more entry, dot text dot star. If I do this, then all such sections can be merged into one text section. I do similarly for RO data as well. For RO data also we can do something like that, dot star. After that, for data section also you can do like that, star. This is a wildcard character. Let's build the project. Let's again run object dump, and you can see that we reduced the number of sections. But still there are some sections, so these sections are related to the standard C library. And for BSS also we can do something like that. Let's go back and let's do dot BSS dot star. That's it. Now you can see that these two sections are pure code sections. They can go into the text section, isn't it? You can see that VMA and LMA are same here because they are codes. That's why you can merge these sections into a text section. You can do that. Let's go to the linker script, and after this line, what I can do is star dot init and star dot finish. This is not mandatory to merge with this section, so you can just leave them like this, no problem. Let's run. Let's check. Now you may be having one question that, in the linker script, we created only text, data, and BSS. How come linker created all these other sections? That's because if there are any unmerged sections, then linker will include those sections as it is in the output file. That's why linker has introduced this section as it is, that is found in the standard C library. So now let's test our application. Before that, we have to do one more thing. We know that whenever the microcontroller resets, the control first comes to the reset handler. And after that, we initialize the data section, BSS section, and before calling main, you have to call a function which initializes the C standard library. And for this purpose, you have to call underscore underscore libc underscore init underscore array. This is a standard library function. It's an init function which initializes the C standard library. After that, you have to call main. Let's call this function. Go to startup file, stm32 startup.c. Let's go to the reset handler here. And here you should call that function libc init array. Let's give the prototype of that. Otherwise, you will see compilation problems. Let's include the prototype of that, void libc init array. That's it. Now you can include a couple of printf statements in your main.c. Anyway, you have these printf statements here. Let's say I write one printf statement here, printf implementation of simple task scheduler. Now the question is, how do you see this printf when the code is running? You can't see, isn't it? Because we don't have any output terminal or output device by which we can see this text message. When you call a printf, newlib calls write system call, which is there in syscalls.c underscore write. In the write, the formatted string is received at this pointer and length is received in this variable. By using this pointer, you can send the data to any output devices you want. As I mentioned, it could be UART or it could be ITM54 or it could be LCD or something like that. But currently we don't have any such devices. That's why currently, even though the control comes to the right, it is just a dummy write. We will not be able to see any printf messages. That's fine. Our goal is to test the code with standard library. Our goal is not to test the printf working, but your code should be fine with standard C library. Code execution should not generate any fault exceptions. Later, we can visualize the printf by using a semi-hosting feature. Let me quit this project. Before testing this project, let me once again open the make file because still some more linker arguments we have to provide. What you should do now here is you should repeat these arguments with linker flags as well. That's why what you should do is just copy this and paste here in the linker flags. During linking also you should mention that because you are linking with a standard C library. After that you have to mention this argument mfloat ABI. This specifies which floating point ABI to use. So the permissible values are soft, FP and hard. This is something to do with the execution of floating point instructions. Sometimes in the project we use floating point related logic, or we use floating point data types and floating point operations. In that case, you have a couple of choices. You can either use the processor hardware floating point unit if supported, or you can use library functions to process floating point operations. Some processors support hardware floating point unit and some processors don't support. For example, in our case, the ARM Cortex M4 processor, it is called as ARM Cortex M4F, where F stands for hardware floating point unit. Our processor supports hardware floating point unit. But before using that hardware floating point unit, you have to enable it first. Otherwise, trying to execute floating point instructions without enabling the hardware floating point unit will cause a fault exception. If your processor doesn't support hardware floating point unit, then you can use the option soft here. Specifying soft causes GCC to generate output containing library calls for floating point operations. That means floating point operations will use library calls or library. In our case, let's not use the hardware floating point unit. Let's just use software libraries for the floating point operations. That's why you have to use this with value soft. Let's use that. Let me copy this, go to the make file. Let's just paste here and mention it as soft, and here as well in the compiler arguments also you have to mention that. Save this make file and make clean make. We don't have any errors. Let's connect the board and let's test this application. So I'm going to launch one more command prompt here. Make load. Let me open my PuTTY terminal. Let's connect to the OpenOCD. Reset init. Flash write image. Erase final.elf. Reset. Halt. Here you can see that we met with a hard fault exception. So the code is not working properly. That is a problem. We have to investigate why this exception is happening. That I will leave you as a small assignment. Just think what exactly we did wrong in this procedure. I can surely think of one thing. The problem could be, let's run the object dump -h final.elf. So here it is. In your reset handler function, when you are trying to copy data section from flash to SRAM, you consider end of .text as start of .data. But that will not be true in this case because there are two more sections are getting introduced right after the .text section. That's why end of .text is not equal to start of .data. You have to take care of this. Just think about that and try to change the reset handler code where you are trying to copy data section. I'll see you in the next lecture.